Still on vector analysis, vector algebra, we are going to talk about unit normal vector. All right, unit normal vector. The unit normal vector n to the surface phi of x, y, and z, which is equal to a constant, is this. The unit normal vector is equal to the grad of the vector field, grad of phi, divided by the modulus of the grad of phi. This gives the unit normal vector n to the surface. All right. Now, the question before us is, find the unit normal vector to the surface, x squared y minus 2yz squared plus y squared z equal to 3 at the point. What we need for unit normal vector is the grad of phi and the modulus of the grad of phi at this point. Now, this is phi itself. Compare it. It is a function of y, x, y, and z. Okay, so based on this, phi is equal to x squared y minus 2yz squared plus y squared z. So let's determine the gradient of this function now. All right. Actually, I have explained this in one of my videos, gradient of a scalar field, how to determine the gradient of phi. Okay, so the formula says the grad of phi is equal to the partial derivative of phi with respect to x times I plus the partial derivative of phi with respect to y times j plus the partial derivative of phi with respect to z times k. All right, so let's determine grad of phi of this function now. We are going to take the partial derivative of this function with respect to x first. So here we are having x squared y. I'll keep y as a constant and differentiate x squared. All right. So differentiating it with respect to x means that we're going to keep all other variables as constant. So I'll keep y as a constant here, differentiate x squared with respect to x, and that's 2x. Okay, this term minus 2yz squared does not contain x. That means it is a constant. Okay, so the derivative of the constant is equal to 0. So differentiate this with respect to x, it is equal to 0. The same thing here. There is no x here. This is y squared z. So the derivative is also equal to 0 times I plus, let's now differentiate this now again with respect to y. That means that we are going to keep x and z as constant. So let's differentiate this first one with respect to y, keeping x squared as a constant. Differentiate y with respect to y, that's 1. Here I'll keep minus 2z squared as a constant, and then differentiate y with respect to y, and that's 1 also. Here I'll keep z as a constant, differentiate y squared with respect to y, that's what, 2y. Okay, times j. And then plus, I'll now differentiate this function now with respect to z, keeping x and y as constant. There is no z here, so the derivative of this is 0. It is taken as a constant. Here, I'll keep minus 2y as a constant and differentiate z squared with respect to z, and that's 2z. Here, I'll keep y squared as a constant, differentiate z with respect to z, that's 1. Times what? K. So the grad of phi is equal to the vector function 2xy plus 0, that's 2xy. 2xy times I plus, this is x squared minus 2z squared plus 2yz. X squared minus 2z squared plus 2yz times times j. And here we have, okay, y squared times 1 is y squared. And minus, this is 4yz, minus 4yz into k. So this is the grad of phi, all right? Now, what is the grad of phi at this point? At the point, this is x, this is y, and this is z. X is 2, y is minus 3, and z is 1. So we are going to substitute the values for x, y, and z into this equation, or into this vector function rather. So the grad of phi is equal to this. X is 2, y is minus 3. So 2 times minus 3 is minus 6. Minus 6 times 2 is minus 12. I plus x squared, that's 2 squared, and 2 squared is 4. Z squared, that's 1 squared, and 1 squared is 1. That's minus 2 is minus 2. Y is minus 3, z is 1. So minus 3 times 1 is minus 3, times 2, minus 6. Y squared, that would be minus 3 squared, which is equal to what? 9. Y is minus 3, z is 1. So minus 3 times 1 is minus 3, times minus 4, that's plus 12. Into what? K. And so what is this equal to? This is minus 12i, minus 12i. 4 minus 2 is 2. 2 minus 6 is minus 4. Minus 4j. 9 plus 12 is 21. Alright, that's plus 21k. So this is the vector for the gradient of this scalar field at this point. Remember I said in the video on gradient of a scalar field that the grad operator will act on a scalar function or a scalar field to produce a vector. Right? So what is now the absolute value of the gradient of phi at this point? So what we just have to do is to take the modulus of this vector. Remember, for a vector A, which is equal to axi plus ayj plus azk, the modulus of this vector, the absolute value of A, is the square root of ax squared plus ay squared plus az squared. So the modulus of this grad of phi is the square root of minus 12 squared plus minus 4, which is the coefficient of j, minus 4 squared, then plus 21 squared. Minus 12 is the coefficient of I, minus 4 is the coefficient of j, and 21 is the coefficient of k. And this is equal to, this is 144, this is 16, and this is 21 squared is 441. So if I add them up, 144 plus 16 plus 441 is 601. Yeah, 601. So this is the modulus of this vector, which is the modulus of the gradient of phi at this point. So we can now determine the unit normal vector, which is the ratio of the grad of phi to the modulus of the grad of phi. So it is equal to, the grad of phi at this point is this, minus 12i minus 4j plus 21k, divided by this, and this is equal to root 601. Root 601. So this is it. What we can see, if I bring out minus 1 over 6 root 601, I'll be having in brackets, this become positive because the minus is out. That's 12i. Okay. Then I have plus 4j and this become minus 21k. Right, so this is the unit normal vector. Thanks for watching this video. I hope you like it. Keep supporting by subscribing to this channel, like and share the video to your friends and to your course mates. I'll see you in the next one.